For my lab, to describe the motion of a falling object, I took a video of me dropping a piece of paper onto the floor and uploaded it into Tracker. Here's the video. Before I could analyze this, I had to do a couple things. First, I had to calibrate my video by using a calibration stick right here. I measured the piece of paper that I was dropping, and it ended up being 5 centimeters, which is converted to 0.05 meters, and meters are the units that we're trying to work with. And then I made a coordinate system. For my coordinate system, I made the origin right where the starting position is of the ball, so the ball would be moving in the negative y direction. You can change this however you want, but I just use this to make it simple. Then I had to track the object's movement by using a point mass function of this, and I measured each point as the ball was falling to come up with these numbers. Then I used VPython. I used the lab2 start function that I got from the video lectures, and tweaked the numbers to fit with my experiment. I found that the standard mass of a piece of paper is 250 milligrams, which comes out to be 0.00025 kilograms, and kilograms are the units we're trying to work with, so I converted that. Then the position of the ball at t equals 0 is negative 0.001 in Tracker, so I use that same number to put as the initial position for the VPython function. I use g equals 9.8. 9.8 is gravity, meters per second squared, so we're going to have to use that later in the function as well. This is the same as our last lab, this area right here, except for the fact that Fnet doesn't equal 0 in this case, so the velocity does change. And Fnet is W plus Fd, and W equals the weight of the ball, which is the ball's mass times g, which is gravity, times j hat, and j hat is just a unit vector facing up, so that's why this part is negative, because the force is going down. The drag force is just the ball's velocity times negative b, and negative b is just a constant that we'll talk about later. So both Tracker and VPython give me y values corresponding to the time, so I used these to make a spreadsheet of the y values and the time against the time. This column right here is the time, and this column right here is the experimental position, which is the Tracker position. And this column is the model position, which is the VPython positions, the positions that we get from VPython. To make them easier to compare, we can make them into a chart right here. The red line is the model position or the VPython function position, and the dots right here are the experimental positions from Tracker. As you can see, the ball that I dropped fell much faster than what the VPython function was predicting, and that's kind of weird. Because of this, I had to make it so that the drag force was very small, because if the drag force was larger, then the gap would only increase. So in my function right here, the drag force is negative b times the velocity of the ball. So I made my b very, very, very small. Here's what the function looks like in VPython when we run it. there's this arrow pointing down, which represents the weight of the force of the weight on the ball, and there actually is an arrow representing the drag force of the ball. We just can't see it because, as I told you, the drag force is so small. There are a couple of possible reasons for the difference in data sets. One, this isn't a perfect angle facing me, and if it's not a perfect angle, it's not a perfect calculation of the data points. Also, when I'm using the tracker functions, it's very blurry as it's falling down because it's falling down so fast. And so I had to try to pick the best point possible to plot in this data set right here. So a lot of it is due to the low quality camera that I'm using. But overall, we get a pretty good model of how objects fall through the air. So if I would have changed my coordinate system, my numbers would still be the same, the magnitudes would be the same. It would just, either change directions or signs. But overall, we would get the same readings. So it's just really arbitrary what we do with this. And also, if I had a better camera, or if we all use better cameras, I could probably get a better reading and my drag force would actually be doing something. But overall, we can see that this is a pretty good prediction of what happens. It's a pretty good model of what happens when you drop something through the air.